Just a reminder, whether it's B or I, it doesn't matter. Eventually it boils down to something that looks like this. And then some source term. And that source term can have a derivative, it can have a current term in it, whatever the case may be. But this will always be our form for our differential equation. Now finding alpha and omega naught, they depend on the circuit. And that's from the KCL analysis. We've done it a few times, certainly the RLC series and RLC parallel, iconic classic circuits. By all means, use our solved problem and take advantage of the fact that we've done those. But deriving alpha and omega naught or determining alpha and omega naught can be quite a challenge. And so that depends on substitutions and recognizing the relationships between current and voltage, capacitors and inductors. It can be a little bit tricky, but it is the circuit analysis. But once we get it in this form, then what we saw last class was we have three possible cases. Alpha greater than omega naught. That was our overdamped case. And then the solution, and again, this could be current, depending on right voltage, but this could be current. It's the same. It can be any component as long as it's the second order. Our solution takes the form AE to the S1t plus A2, e to the S2t, plus in here I could just write particular. And so in the particular solution, again, depends on the source. As we've looked at our step function source so many times, and we'll continue to do so, that's going to be a constant. So for our step function, that's going to be constant. But we've seen cases where that was not a step function source. We did a small problem like that in the last homework, and we'll look at it again. But for the large part, we'll do step functions just because we can do them in a reasonable amount of time. Something to remember here, S1 and S2 are less than 0. They are negative. Otherwise, that would be exponentially growing, which would be kind of a cool circuit, but problematic. So voltage exponentially growing would eventually create damage and excitement. So these have to be negative, of course. And then we have this kind of special case, alpha equals omega naught. We call this critically damped. And we talked about this a bit in the last class. What this really is the boundary between overdamped and underdamped. It doesn't really exist, but because it gives us more math problems, we take advantage of it. And so our form looks something like this. A1 e to the minus alpha t, and that's just in there directly. And again, that's the alpha that depends on the differential equation. Plus an A2, t e to the minus alpha t. And again, a particular, which again is going to be a DC term when we talk about step function sources. And then finally, we can look at our third case, alpha less than omega naught. And so we're underdamped. And it's worth noting S1 and S2 are now complex. And to be a little bit specific, since we can write this beta, we used this last week, as omega naught squared minus alpha squared, square root. And S1 could be alpha plus j beta, and S2 equals alpha minus j beta. And that came out of the quadratic expression I had so much trouble with last class. But if you look at S1 and S2, they have a mathematical relationship that will come into play a little bit after spring break and more in Unit 3. Anybody recognize There's a mathematical relationship here with regard to complex numbers. That's kind of a label. Was that? Yeah, it's a complex conjugate pair. And it doesn't matter just yet, but we will use it when we start talking about Laplace actually on Thursday. So it's a complex conjugate pair. And so not something vital to know right now, but in the near future, this means complex conjugate. And essentially, if you haven't heard of that before, when you take the complex conjugate of something, you just change the sign of the imaginary term. It's that straightforward. So if we have something that's S1, as we have above, equals alpha plus j beta, the complex conjugate of S1 is alpha minus j beta. Again, just a little drift on the side, but something to be familiar with if you haven't seen it before, and a reminder. So anyway, we have two forms we can write this in. The first one, not very practical, at least as far as solving things easily, but since I tend to use it occasionally, I'll write it out. E to the minus alpha t, e to the minus j beta t. And you can multiply those together, of course, clean that up a bit. And then ma2, e to the minus alpha t, e to the plus j beta t. And there's our complex conjugate pair as arguments of the exponentials. So again, you can multiply those together. We wrote them slightly different last week. And then again, a v particular. So, and we can write it like this, but the problems we'll solve with our differential equations, it's a little bit easier to write it as e to the minus alpha t, a1 cosine beta t plus a2 sine beta t plus v particular. And these are equivalent if we apply trigonometric identities and Euler's law and whatnot. We can go from here to here, but this is really the one we're looking at. And so out of all these cases, and we did this last week, it's worth boxing up our solution form. And again, I've said this several times already, but when we look at step function sources, our particular solution is a constant. And that's where we kind of left off in the last class. And so to dive in here and think about things a little bit, let's consider our circuit. Now we've represented in general form, we need to find those coefficients. So how do we find A1, A2, and the way we've been writing it so far, be particular? Well, let's take advantage of one of our options. Let's look at step function sources. In which case, v particular is just a constant. It's the same form, we'll call it A3. You can use a different constant if you're so inclined. And so, well, let's again look at overdamped. It's a nice starting point, and our solution looks like v of t, a1, e to the s1t plus a2, e to the s2t plus a3. And again, reminder, s1 and s2 are negative. To write them out, s1 equals minus alpha minus alpha squared minus omega naught squared. And S2 equals minus alpha plus alpha squared minus omega naught squared. And that was, again, a quadratic expression we looked at last week. So we have this in our notes already, but just to remind ourselves of what they are. So, how do we find A1, A2, and A3? Well, this is the second order differential equation. We find A3 using any particular solution method. In this case, we can find A3 from the DC steady state expression. And so again, that depends on our circuit. If we're looking at the RLC circuit and the voltage across the capacitor, it would be the voltage across the capacitor as time goes to infinity. And a comparable relationship when we look at the parallel circuit, and we'll do this in particular. And so, well, what about A1 and A2? And just to, I guess, prove this, why does this work? Well, C of t going to infinity equals A1 e to the S1 infinity plus A2 e to the S2 infinity plus A3. But remember, S1 and S2 are less than 0. So what happens to these guys? They go to 0. And there's our DC steady state analysis. So the voltage across whatever component we're looking at, or again, likewise, if we were looking at current, whatever that value is from our DC steady state analysis, that's directly A3. Since it's second order, as we said, well, what else? These are initial value problems, so we need a VT equals 0 plus. And so what do we wind up with here? Well, that's A1 e to the S1 0 plus A2 e to the S2 0 plus A3. And so we wind up with A1 plus A2 plus A3. And again, if we were looking at a different type of source, well, we would already know our particular solution function, so we could plug that in and get a direct number here. But effectively, this is known from above. We can write it out in general like we are right now, but this becomes a known value once we get to this step. And so this is an initial value problem. Depends on the circuit, depends on the component we're looking at, of course. And so, well, our second term must be 0 plus by dt. And we can do a little bit of math here. We wind up with S1, A1, e to the S1, 0, S2, e to the S2, 0, and then 0 once we differentiate. Again, we talked about DC steady state step function sources, so this term vanishes, and we're left with just S1, A1 plus S2. Oh, and I left off my A2 in there. Important A2. And that's it. 2, 3, and 1. We had 3 unknowns. We have 3 equations. One from the DC steady state, which is the solution of a particular form, and then 2 from our initial value. And so there's the overdamped problem for our DC steady state expression. Step function sources. Overdamped. We wind up with 3 expressions. A3 is the DC steady state term. A1 plus A2 plus A3 equals V of 0 plus or I of 0 plus. Again, whatever we're looking at, whatever the case may be. And then S1, A1 plus S2, A2. And the S's are known. Those came out of the directly out of the differential equation. And here we have to know a little bit about our circuit, of course, to find these values. VI 0 plus. And this is, again, the same. It doesn't matter what we're looking at. That's the form. So once you have the differential equation, here's the way to find the terms when it's an overdamped circuit. And so let's consider a case study. And let's go with one of our classic circuits, 5 to do T. So we have an R, that's my R, 400 ohms, 10 to the minus 3, 10 to the minus 7. And so, what are we looking at? That's, of course, R, L, and C. Well, this is an RLC series circuit. And you are, of course, invited to derive the differential equation yourself. But me personally, let's say we're looking at the capacitor voltage. We'll start there. We'll look at the resistor and the inductor as well. This differential equation has this expression. In this case, B source is 5, and so this is a familiar form. Remember, this is 2 alpha, and this is omega naught in our general second order differential equations. And the mechanical engineers use the same formula, the civil engineers, everything winds up the same. So just because we're looking at circuits, this is the general expression. And so we can do some math in here. 400 over 10 to the 3, 10 to the minus 3, equals 2 times 10 to the 5th. Oops. Alpha equals 2 times 10 to the 5th. Do that right. And then we can look at omega naught, 1 over LC, which I hope we agree is 10 to the 5th. Square root. So, like we've fortunately just been looking at, alpha is greater than omega naught. And so that's overdamped. There's our first case. And we can go and find our S1 and our S2. And figure them out. So, S1 minus 2 times 10 to the 5th minus square root of 2 times 10 to the 5th squared, just to write things out, minus 10 to the 10, which I hope is minus 4.23 times 10 to the 5. And S2, not to write out in as much detail, minus 7.68 times 10 to the 4. And there's our two expressions, and now once we know our S1 and S2 and we know it's overdamped, we can very quickly go straight to our solution form. BC of t equals A1 e to the minus 4.23 times 10 to the 5t plus A2 e to the minus 7.68 times 10 to the 4t plus A3 because it's a step function source. What's the voltage across the reason? Yeah.
When you found omega naught, where did the square root come from?
It's omega naught squared. Did I not write that? Ah, sorry. I left off my square here. Oh. 2 alpha plus and then omega naught squared. Did I do that before? So the zeroth term is always omega naught squared. The first order term is 2 alpha, and the second order term is 1. So, and just to emphasize again, we have to get a coefficient of 1 on this term in order to get 2 alpha and omega naught squared. So you got to clean this up. Coefficient has to be 1 here. So, there's our expression. Just to ask the question, what form is the voltage across the resistor going to have? The solution form. What's that going to look like? No one wants to guess? It's the same. Doesn't change. It has to be the same. The homogeneous terms are the same. It has to have the same form. So we could write VR of t equals the same. VL of t equals the same. I C of t equals the same form. Of course, the coefficients are all going to be different. So maybe you want to use B1, B2, and B3, C1, C2, and C3, but the form is going to be the same. Coefficients, of course, are going to be different. But the form is going to be the same. It has to have the same exponential response. So, where do we go from here? Well, in our initial definition, we have a 5-volt source that turns on at t equals 0. The source equals 5 u of t. What does this imply for us? Well, our DC steady state, DC as t goes to infinity, equals 5. I hope we all agree on that. I've done this circuit quite a bit, but the capacitor opens, the inductor shorts. As we let it go to DC steady state, if that's an open circuit, no current's flowing, the voltage across the resistor is therefore 0, which means we have 5 volts here. What else does this expression tell us? We have a source that turns on at t equals 0, so what are our initial conditions? 0. And so we also know VC 0 plus equals 0, and IL 0 plus equals 0. Why is this one important? Well, that's an L. Well, that's also IC 0 plus, which is what? Well, that's C dV 0 plus by dt, which in this case is 0. So this is our initial conditions telling us what our differential terms are going to be. And that's where the circuit analysis comes back into play. So we have to go back to the circuit to determine our VC and our, well, that's a dVC by dt, our initial conditions and our derivative initial conditions. So we now know A3, of course, VC of t, A1, e to the minus 4.23, just to rewrite it, 10 to the 5t plus A2, e to the minus 7.68, times 10 to the 5t plus 5. And we now just went over and said we had 0 initial conditions, so VC 0 plus equals 0, equals A1 plus A2 plus 5. And in this case, dVC 0 plus by dt equals 1 over C IC 0 plus, just to write this out again, equals 1 over C IL 0 plus, which we know is 0. I didn't leave myself much room, so 0 equals, well, minus A1 4.23 times 10 to the 5, minus A2 7.68, that was supposed to be 4, times 10 to the 4. And we have 2 equations, 2 unknowns. You can punch that in your calculator, of course, or however you're so inclined. Find those values. And what I found was A1 equals 1.1 and A2 equals minus 6.1. And if we plug that in up above, we have a solved problem. 1.1 e to the minus 4.23 times 10 to the 5t, oops, minus 6.1 e to the minus 7.68 times 10 to the 4t plus 5. And there's our voltage as a function of time. Does it check? Well, we can certainly plug in t equals 0 and get that equal to 0. So that's always a good check. You can do that fast by inspection. Certainly you can differentiate it and check that as well. Hopefully that's correct. Though it's not guaranteed that I didn't make a math mistake somewhere. There's our expression. What does this look like? It's an exponential growth. It's always good to plot things. Oops. There's v, there's 5, there's time, and there's our overdamped case. Exponentially converging to 5 volts. Not so different than our first order circuit. We have a slow exponential growth. That's fairly normal. Everybody okay with that? I wrote down a lot of numbers. I won't always do that, of course. So, let's look at a more extreme example. So this is overdamped. We wrote that early on. And that has the overdamped characteristics. So, in the example we just did, R was 400. Let's really crank up R. Make it 5K. Observationally, and we'll use the same L and C. Observationally, just kind of physically, how do we expect this to behave? You increase the resistance. What do you expect with the charging of the capacitor? It's going to be slower. It takes longer to charge up. Electrons move slower, or however you want to say it. So it's a slower charge. So we increase the resistance. It takes longer to charge up the cap. Effectively, what are we doing? Well, we're making the circuit more overdamped. And so if we go through here again, we have omega naught equals 10 to the 5th. They're the same L and C, 1 over LC square root, still 10 to the 5th. I probably should put units in there, radians per second, just for completeness. And we have an alpha, that's 4.998. Oops, so, wrong alpha. 2.5 times 10 to the 6. And so what we see here, alpha, much, much larger than omega naught. Now, more than an order of magnitude. And that's reasonably accurate to say greater than 1 magnitude, much, much larger. So what can we say here? This is strongly overdamped. So strongly overdamped. And so that's something to consider. The larger alpha is relative to omega naught, the more strongly it's overdamped. That has some implications if we look at our S1 and our S2. S1 minus 4.998 times 10 to the 6, and S2, 2 times 10 to the 3 minus. And I just plug those into the quadratic expression. We saw that a minute ago. I don't need to rewrite out what that is, but it comes out of that minus alpha plus or minus square root, alpha squared minus omega naught squared. Well, looking at these terms, if we think about what's going on here, and just to write out the final answer, we get something that looks like VC of t 0.02 e to the minus 4.998 times 10 to the 6 t minus 5.002 e to the minus 2 times 10 to the 3 t plus 1. Neglecting the coefficients. I mean, certainly A1 is much, much smaller than A2, but a little bit more interestingly, what can we say about this term relative to this term? What can we say about the exponential behavior of this guy relative to the exponential behavior of that guy? I couldn't quite hear you, but I think you said it. You still faded off at the end, but I think you said it gets smaller faster. So, and that's what happens when you have strongly overdamped cases. So this term is 3 orders of magnitude larger than this term. Well, in exponential concepts, that's huge. So this guy goes to 0 really, really fast relative to this guy. And so, well, this guy, you know, if you were to draw out an exponential plot, it looks like that. Whereas this guy, you know, this isn't drawn to scale, of course, but it looks something like that. So, in some sense, this term is negligible. I mean, not only is the coefficient small, but the argument, the exponential argument, is huge, and so this term vanishes very quickly. So relatively it's small. So when we look at our plot, our result looks fairly similar. It's still an overdamped case, still converging to 5. Well, what is this curve? This curve is approximately really just 5 minus, 5 e to the minus 2 times 10 to the minus 10 to the 3t. So you can actually look at the curve, from the curve directly find one of your roots. In this case, the dominant root. This guy, much, much more significant in terms of behavior. This guy fades out somewhere around here. Stops contributing. Again, not even factoring in the coefficient. And this coefficient could be much larger, perhaps. Depends on the initial conditions. But this term vanishing small. So when you get a plot, when you get some characteristic response that's second order but strongly overdamped, it behaves like a first order circuit. And from that first order expression, you can do the same analysis that we did in Lec10 and Lec5, or 5 and 6, or whatever it was, where you looked at the plot, you found the RC time constant. Well, the RC time constant is essentially 1 over alpha, 1 over s in this case. So you can find that directly from the curve as well. Another thing to look at here, even comparing, here's our previous example. We can clearly see this converges much more slowly than this does. So our transient response, these guys are, this is our previous example where we had 400 ohms as our resistor. So these guys, S1 and S2, much, much larger than this. This goes back to what we said physically early on. Our transient terms fade away more quickly as that resistor gets smaller. As the resistor gets larger, this term gets larger. As that resistor goes to infinity, well, we just go straight up to 5 volts. So that term becomes extremely large. So, things to think about. Strongly overdamped, low response, only one of our S's, only one of our roots matters really, the dominant root, so to speak. And we'll see a comparable situation, though not quite the same when we look at underdamped. Everybody okay with this? Questions? Now to go back to the question I asked earlier, if we look at either of these circuits, 5U of T, it doesn't matter which one. We can do this one. Well, what about VR as a function of T? Well, we already kind of wrote this out. We know what the form is. We already discussed this, but we have an E1 minus 4.23 times 10 to the 5, T plus A2, e to the minus 7.66 times 10 to the 4 plus A3. Well, how do I find A1 and A2? And A3 for that matter. Well, the same procedure. A3 from the DC steady state. And what's that in this case? If we're looking at the voltage across the resistor, what's the steady state voltage across the resistor? 0. Right? As we let it go to steady state, the capacitor opens, the inductor shorts. Because the capacitor is open, once again, no current is flowing, so A3 in this case is 0. And by the same reasoning, do we know VR 0 plus? Well, what's VR 0 plus? Well, DL is what? LDIL by dt. Well, what's IL? LC. And so, once we know the voltage across the capacitor, which is the easy one to get, again, you know everything. Rather than attack this by looking at second order derivatives to find out initial conditions, do the straightforward expression. Do the simpler calculation. Certainly we can differentiate fairly safely, I hope. So, this is the guy to get, and it gives us everything. It gives us current as well. All right. So, we looked at overdamp. Let's start the journey into critically damped. Any questions on that? So once you know one component, again, to emphasize, you know everything. You get everything else from that. Critically damped case. Let's again look at our familiar RLC series circuit. 200. 10 to the minus 3, 10 to the minus 7, 5 t. What are we left with? Well, alpha is R over 2L, 200 over 2 times 10 to the minus 3, and lo and behold, that's 10 to the 5th. Omega naught, square root of 1 over LC, and again, 10 to the 5th. Yes, it's quickly checked. And so I did pick the right numbers. What's our solution form? dc of t, A1, e to the minus alpha in this case, 10 to the 5th t, plus A2, t, e to the minus 10 to the 5th t, plus A3 because we have a step function source. And the same reasoning applies. So this is getting a little redundant, but our DC analysis gives us A3, which is 5 volts. Right? And so, well, we have again a zero initial condition problem, DC 0 plus equals what? Well, this nice thing about the critically damped case, we get equals, in this case, 0, because our initial condition was 0. DC 0 plus. So for the critically damped case, things fall apart fairly straightforward. DC steady state for a step function gives you A3. Initial condition gives you A1. And again, you can name the constants what you want. In this case, A1 equals minus 5. And then dVc by dt. I guess a little bit exciting. We have to do chain rule differentiation. It's probably been a while since we've done that. A1 minus 10 to the 5, e to the minus 10 to the 5t, plus A2, e to the minus 10 to the 5t, plus A2t, minus 10 to the 5th, I'm just writing everything out. Plus 0 if you want. When we differentiate the constant, of course, again, if we had a particular solution term in there, we'd have to use that. Well, evaluated at t equals 0, plus, that goes to 1, that goes to 1, and that goes to 0. So what are we left with? A2 minus, if we want to call it just more generally alpha, A1 equals dVc 0 plus by dt. So there's our form. And again, if we have 0 initial conditions, no guarantee we have 0 initial condition. Our 0 initial condition in this particular circuit comes out of the fact that the current through the inductor is 0, because this relates to 1 over C, IC 0 plus, which we know is 0. So there's our A2 term. And so the critically damped case kind of falls out. The math is a little bit more straightforward. You wind up with dC of t equals minus 5, e to the minus 10 to the fifth t, minus 5 times 10 to the fifth, t e to the minus 10 to the fifth t, plus 5. And there's our DC steady state. Initial conditions check. We can go ahead and make the derivative. What does our plot look like? Well, again, it looks something like this, but the rise time is a little bit faster. So you look at that term, these exponential terms are decaying faster than they were for our overdamped case, of course. Things are rising faster. We're charging more quickly, so critically damped is charging more quickly than overdamped. And so again, just to summarize what we looked at here, critically damped case, how do we find our constants? A3 from DC steady state. Again, this assumes step function source. Which we look at a lot. A1 from our initial conditions. A1 plus A3 equals VC 0 plus. And what we wind up with is minus alpha A1 plus A2 equals dVc 0 plus. And again, that's the current expression. Those are the three expressions we look at for the critically damped case in the RLC series circuit. Now, it's worth pointing out, this is the RLC series circuit, but this is valid for any circuit. It's just what's on the right side changes as we look at a different circuit. This is the circuit analysis. This just comes out of the map of our solution form. Am I moving stuff away too fast? Say something. This is like the quietest class I've ever had. Say something. By now, most people say, most classes will slow me down if I move too fast. excitement for tomorrow. Those of you who have that to look forward to. It's not an easy exam. So, all right. So now, under damp case.
Oh no, that's
Are you scared?
Well, you're electrical, right? You're just electrical?
And again, if we look at our RLC parallels, our RLC series circuit, nothing's changed. 5 U of T, we're bored. 50, 10 to the minus 3, 10 to the minus 7. We can go through the math here. What do we discover? Omega naught is still 10 to the 5th. That has not changed. Alpha is 2.5 times 10 to the 4. Well, we recognize alpha is less than omega naught, which implies underdamped. Once we're underdamped, we do want to find beta, which is the square root of omega naught squared minus alpha squared. And again, if I did my numbers correctly, that's 9.68 times 10 to the 4 in this column. And I've been leaving units off, but probably should get away from that. So, what is our solution form? BC of t equals e to the minus alpha t. Alpha is known, 2.5 times 10 to the 4 times an A1 cosine beta t, which is again known, 9.68 times 10 to the 4t, t plus an A2 sine 9.68 times 10 to the 4t, close bracket, plus an A3. That's outside the bracket, of course. And again, to emphasize, this is an exponentially decaying sinusoid. And in my experience, it's a fairly confusing expression. So we'll look at that pretty closely. How do we find A1, A2, and A3? The same way we looked at all along. So A3, DC steady state. No problem. Because our exponentially decaying sinusoid terms vanish as t goes to infinity, it's the t going to infinity situation. That's what DC steady state is. And so we're left with just A3. This guy goes to 0, making all the bracket go to 0, of course. We can then look at our initial conditions, BC 0 plus. What are we left with? Well, we plug in, oh, there's a t up there, of course. E to the 0, A1 cosine 0, plus A2 sine 0, plus A3, and if we do this correctly, that's A1 plus A3, because sine 0 is, of course, 0, and cosine 0 is 1. So there's our second expression. And then dVc by dt, well, we can do this symbolically since it'll help me write a little bit faster, but we wind up with minus alpha, e to the minus alpha t, A1 cosine beta t, plus A2 sine beta t. So again, chain rule differentiation, plus e to the minus alpha t, minus A1 beta sine beta t, plus A2 beta cosine beta t, all evaluated at t equals 0 plus. And so I didn't put the numbers. We know what beta and alpha are, of course. And so what are we left with? Well, equals minus alpha A1 plus beta A2 equals dVc 0 plus by dt. Again, whatever that may be. In this case, we have 0 initial conditions. That was a little bit fast, but all I did was differentiate our general expression as alpha and betas. So you could plug in numbers for alpha and beta. I just didn't want to waste the ink. Red ink is valuable. So here's our general expression. Once you know alpha and beta is, what alpha and beta are, you can find all our coefficients, of course. A3 from the steady state. And again, it becomes a fairly mechanical problem. This generally applies. So, once we have an underdamped case, you can write these down. These are boxable, in some sense. Once it's underdamped, this is true. And the same was on the other ones, even though I didn't write it. I should leave VC0 plus outside because that could be current, that could be anything, but that form, we're going to wind up with A1 plus A3. And then this form, I'll leave the DVC0 plus outside. But it's always going to take this form. So that's, again, the beauty. Once you go to the circuit, in this case a simple circuit, but once you find the expression for the differential equation and find the expressions for alpha and omega naught, it is a solved problem. Initial conditions, find those from the circuit analysis, and you are good. So the same with the other guys. I put the critically damped cases here. If you want to scroll back on the notes. Again, the particular thing we're looking at may vary, but that form will always be true. And the same with the overdamped case as well. We saw that. And so what do we wind up with here? I did the math already, and again, hopefully I'm correct. DC of t winds up being, for this particular problem, minus 5, either minus what was it, 2.5 times 10 to the 4, t minus 5 cosine, 9.68 times 10 to the 4 t, and then minus 1.29 sine, 9.68 times 10 to the 4 t, plus 5. So there's our DC steady state. And what does this look like? Well, things are perhaps getting a little bit more exciting. There's 5 volts again. There's time, DC of t. This has a rise. I didn't check, but this may actually go above 5 volts, oscillate a little bit, and then eventually converge. And that's where the ringing comes into play. We talked about that last week. So this is an underdamped case. Underdamped means it oscillates. It oscillates or rings about the steady state value. Not very much in this one. So arguably we could say this is weakly underdamped. Probably wouldn't be able to hear it if you put it up to a headset or something. On the other hand, what happens if we reduce R? So again, same problem. We love this circuit. 5 ohms. What can we say about this? Well, again, omega naught, 10 to the 5, alpha, in this case, 2.5 times 10 to the 3. So almost 2 orders of magnitude smaller, alpha much, much less than omega naught, strongly underdamped. And And so again, we can plug in the calculations, but beta is about 9.9969 times 10 to the 4, or more than 1 order of magnitude larger than alpha. Effectively, what's going on, and we can finish that out, find out what the A1, the A2, and the A3 are, but that's getting fairly mechanical, I hope, and not very exciting. What are we looking at here? There's our 5 volts. I should have drawn it as a dashed line. We're getting a lot of oscillation. We have a very fast rise time. We're getting something that looks like this. It's a decaying sinusoid, but a lot of ringing. So effectively what we're saying is the more strongly underdamped we are, well, here's our exponentially decaying term, e to the minus 2.5 times 10 to the 3. That's a slow decay. We've seen that in a strongly overdamped case. So that's a slow decay with a lot of ringing. So these can be bigger. It depends on, again, on the initial conditions. So lots of ringing as it decays slowly. As we make the circuit more and more underdamped, then the ringing just keeps going. So think about it, well-designed bell, you hit it, it rings for a long time, or a tuning fork or something like that. Good quality tuning fork, you hit it, you can hold it for a couple minutes, maybe still hear it. The poorly designed tuning fork made of wood, not so very long. So that's what we're seeing here is a lot of ringing with small decay, slow decay. So strongly underdamped, long ringing. To look at this curve in particular, and I want to draw it a little bit bigger. This is what you saw perhaps when you did the derivative of the step function. So this was a couple weeks ago in lab, but you took the derivative of that. What should the derivative be? Well, it should be something like this. Right? I mean, ideally, in a mathematical sense, you get delta functions at each of the transitions with whatever the appropriate sign is for the circuit. But in fact, what did you see? You saw something that looked like this. And then if you had them too close together, it never went to 0. And so where does this come from? This comes from the LC resonance. So this is a second order or higher. It could be higher than second order. Second order response or higher. You have that resonance, it doesn't behave very well. There's a discharge and charge. There are some mathematical situations with regard to the step functions. You'll see those perhaps in a future class. But actually making step functions is non-trivial. You cannot actually really make them perfectly. And part of that has to do with the Fourier expression for the ringing. So this is an artifact everywhere. Every circuit you have always has some capacitance and some inductance. Typically capacitance dominates. Those things get smaller and smaller. Inductance is becoming a bigger factor as well. Historically it was ignored, but that's no longer true. And so a lot of second order responses, ringing exists. And the same thing with the overdamped case. So one of the limitations on digital electronics is called rise time and fall time. And you actually saw that in PSpice when you implemented the pulse. As part of the specs for the pulse, you had rise time and fall time. I told you to set it to 0. So we had idealities. But really, when you apply a voltage input to an op-amp, for example, it takes some finite amount of time for the op-amp input to reach that voltage, to reach that applied voltage, because there's internal capacitance. And so that finite time slows the switching speed. It gives you an upper limit of how fast that op-amp can behave. And then when you get down to transistor level, that's a big factor as well. Look at this curve in a little bit more detail. I'm going to draw slightly different. What could this possibly be in the RLC circuit? For a step function source, it turns on at t equals 0. So what could this be? Well, it's definitely underdamped. But what could I be measuring? To be specific. So if I have u of t, it could be VR. I agree. What else could it be? Could be VR, could be VL. Maybe one more thing. Yeah, well, not for a step function that turns on. It's not going to be VC. IC. So it could be any of these. An initial condition that's 0. Now, actually, one of these we can rule out. Which one is it not?
VS.
Well, it's not VS, that's true. But no, out of these three. One of these it's not. For this particular source, what is it not? This goes back to our initial condition.
DL.
It can't be VL because when you do the KVL analysis, our initial condition, again from homework or problem 1 on the homework, the voltage across the inductor is not 0 at t equals 0. And actually, I've had that as a test question before, so it's not that one. So it can't be that one. When we consider the t equals infinity, yes, that's possible, but now we can rule it out when we look at the initial condition. It can be both of these. Why? Well, these are linearly related because it's the voltage across the resistor, so that has to be consistent for this circuit. Looking at this circuit, there's a period to our oscillation, and that's fixed. So this goes back to, I don't know, whatever math class, physics 1 or physics 2, something like that. That's the period. It's the time between peaks, the time between nulls, however you want to say it. That's the period of oscillation. Well, beta has a nice relationship, 2 pi over the period. So physically, in our circuit, if we know beta from taking the omega naught squared minus alpha naught squared square root expression, we can find the period, and then we can find the oscillation. Again, this is an exponentially decaying sinusoid. Beta is, or t is our period in our sinusoid. Where's our exponential? I draw the mirror image. Those are both the same exponentials. One's the negative of the other. What is this dashed line? This is V naught e to the minus alpha t. And this guy's minus V naught e to the minus alpha t. So as we look at experimental data, and I didn't quite draw that very perfectly, this exponential envelope should touch every peak. Bring that down a little bit. So how do I find beta and alpha from an experimental result? Well, beta you can get from the period, which you can measure. Certainly you can locate 2 peaks. Our discovery board lets us do that nicely. You can find the period. Everybody knows what 2 pi is, 6.28 and change. And then you can invert that and find beta. You can go back to the circuit and find out if they're consistent. What I've found in the past is finding alpha a little bit more tricky. It seems more challenging for students. If you have 2 points, you know this expression. Effectively, this is a general form for an exponentially decaying signal. The peaks always lie on the positive, or if you want to use the negative expression, the peaks touch the exponential curve. So when I say exponentially decaying sinusoid, effectively what the exponential does is it determines the amplitude of the sinusoid at a given point in time. And it's decaying, of course. It's getting smaller. So that exponential is the amplitude of the sinusoid. This effectively comes out of our A1 and A2. And so how do we find alpha? Well, there's two unknowns here. 2 points, T2, T1, V2, V1. Plug them into an expression, find alpha. You know T, you know voltage. This is some voltage as a function of time. So it's a plug and chug. You'll see this in the lab on Wednesday, but I've historically seen students have a lot of problem with it. You'll see it again, those of you who have to take fields, exponentially decaying waves in that class as well. And no matter how many times I've taught this, it's always been a bit of a challenge. So being able to recognize what you see here, very, very helpful. Fairly likely you'll see this in exam settings in various classes, including this one. So, there's a little bit of math. Just like in the strongly overdamped case, we looked at one dominant root. Well, and that gives us something we can use or compare to measurement. Here, you can directly measure using the discovery board, period. You can find these exponential values, and so you can compare this. So a little bit of math back and forth, but comparing measurement to circuit calculations, very, very reasonable. In the interest of saving a little bit of time as we do the team assignment, we did this last class, but what does our differential expression look like for the current through the inductor of DIL by dt plus 1 over RC DIL by dt plus 1 over LC IL equals 1 over LC on the source. It's the same. What's 2 alpha, or what's alpha? 1 over 2 RC. This is now a solved problem. Omega naught, 1 over LC square root. Or if you want to use square root terms. So we derived that in the previous class. Again, it's a classic circuit. Once you have it in this form, you know alpha, you know omega naught. For given values, it now becomes a solved problem. All those expressions that we boxed up a few minutes ago, wherever they went, whatever the case is, these type of things, for underdamped case, for critically damped, etc., they apply. Yes, we're looking at current now. It's a solved problem. All you need to do is know the initial conditions. All right, with that in mind, let's do a team assignment.